Okay, everyone. So welcome. We are now finishing week 11. This is class number 22, and we are going to today we are going to review for the test next week, and it will be on um, chapters 7 through 14. So here we go. If you're so wow. Okay. Wow. All right. So chapter 7. Each student. Okay. Okay. So just quickly, I'm not going through these in depth. There's 7 or 8 chapters. I'm just going through like the important stuff. Jose, you're here. Okay. I'm off that page, but remind me in case I forget. So we had some examples of expected value leading up to the formula. So all these were just different examples in different situations. So here, finally, on slide number 9 is the formula for the expected value. Okay, this formula is used for expected values and also for fair values, okay? Because if something is fair, the expected value should be 0. You shouldn't expect to get anything. You shouldn't expect to give anything. So that when you calculate the expected value, it should add up to 0, okay? In general, what is the expected value? You look at the possible outcomes X of an experiment. You multiply each one times the likelihood that it occurs, X times its probability, and you add them all together. That's the formula for expected value. I'm not teaching this. I'm just reviewing it. I'm explaining what you need to know, okay? So expected value and fair play, that's it for chapter 7. Okay, so if you understand expected value, there's nothing in chapter 7 I can possibly ask you that you hopefully should not be able to answer. Remember, the solutions are all up all the way through 14. So you can look at any solutions to any of the homework questions. And let's go now to chapter 8. So chapter 8 was on randomness, runs, and coincidence. Essentially, the idea of chapter 8 was that randomness is not necessarily what you expect to see. The conscious understanding of randomness is no pattern. But if something is truly random, then you should expect to see some patterns every now and again, because in a true random situation, patterns will show up as well. Hold on. Dad, can you close the door? Dad? Can you close the door, please? Thank you. Okay. So you should expect to see sequences of what you would call non-random occurrences, like lots of H's in a row or lots of T's in a row, what we call runs. Okay, truly random things have runs. So what do people think the word random means is not necessarily what random truly means. And this lends itself to 2 erroneous beliefs. These 2 beliefs are not valid. There is no real law of small numbers, and there's no real law of averages. Okay, by the law of averages, there's no such thing. The law of averages is nonsense. It's something people say to look smart, and in reality, they're looking stupid. Okay, there's no such thing as the law of averages. Oh, well, I got a lot of heads, so by the law of averages, I'm going to get a lot of tails. That's nonsense. Okay, if you get a lot of heads, either it's not a fair coin, or it's 50-50 on every flip. So there's no such thing as the law of averages. There's no such thing as the law of small numbers. Oh, well, yeah, small numbers, you expect to have this. No, with small numbers, you expect to get nothing. Okay, because anything can happen. What you do have is the law of large numbers. The law of large numbers is a mathematically proven fact about what you should expect to see in the long run. And that is that it should narrow in, the proportion that you're getting should narrow in on its true value, whatever that true value is. So we had a lot of that. We did a lot of examples, talking about those 2 sequences and the iPod shuffle, right? The whole idea of truly randomness means that you should expect to get the same song multiple times in a row, because in a random situation, runs happen. So they had to build in specific technology not to let that happen, i.e. they made it less random, not more random. More examples. Let's not forget the multiplication rule for independent events from a previous chapter. But even though it was from a previous chapter, it doesn't change the fact that it still has to hold. And that is that if events are independent, that you calculate how many ways the first one can occur, how many ways the second one can occur, and you multiply. So for example, if I have 10 pairs of pants and 3 shirts, and I have to decide, hey, what am I going to wear today? Well, I have 30 outfits because each of those 10 can match, if you ignore fashion, with any one of those 3. 10 times 3 is 30. The same thing holds with probabilities. If there's a 1 in 6 chance this can occur and a 1 in 5 chance this can occur, and they're independent, there's a 1 in 30 chance. I just multiply 1 over 6 times 1 over 5, and that gives me the chance that both of them occur, because when things are independent, we just multiply the events. Again, not teaching, just telling you what you have to know. Don't worry about the birthday paradox. It was a little confusing. And that was it for chapter 8. Again, quick review. So what's chapter 8 about? It's about randomness, the fact that you should expect runs to occur even though they don't seem random, that the human conception of randomness is not necessarily what's really true. The law of small numbers does not exist. The law of averages does not exist, but the law of large numbers is a wonderful thing. Okay, so that takes us to that chapter 8. And stop me at any time if there are questions. I'm running quick because I want to make sure we cover everything. But if there's questions, please let me know. Then we have chapter 10. Chapter 10 was on displaying quantitative data. We know there's 2 kinds of data. There's categorical data and there's quantitative data. Categorical data is categories: blue-eyed children, red and hazel-eyed and brown-eyed, California, Idaho, Iowa, Arizona, etc. Categories. And then there's quantitative data, numerical, where numbers and math make sense, like heights and weights and scores and incomes and ages and things of that nature. And the way we display them is completely different. So this chapter is displaying quantitative data. And we saw that there were essentially 3 different ways of displaying quantitative data. And the first method was by what's called a dot plot. What is a dot plot? Well, it's on the x-axis, you list every possible outcome. And then on the y-axis, you make a dot for how many times for each time it occurs. So if 10 occurs 19 times, you'll make 19 dots. Try to have the dots the same size so that the heights kind of corresponds to how many you have. If you have big dots here and small dots here, it's going to kind of skew up your perceptions. But dot plots are fairly self-explanatory, I would hope. And then, of course, there's bad dot plots, numbers not in order. Okay. And then we have a histogram. So a histogram is similar to a dot plot. The difference between a histogram and a dot plot comes into the fact that with a dot plot, you actually list all of your actual values. And with a histogram, you're collecting values that fall in a given range and you're putting them into a bin. What's the disadvantage of using bins is that you lose the data itself. You just kind of know, well, it's in here somewhere, but I no longer know what it is. Why is that a good thing? Because if I have a million pieces of data, I can't make a million dots. But I can say 92,000 fell in this one, 117,000 fell in this one, and so on. That I can do. And the heights of the histogram are the frequency, how many it occurred. So for this example right here, that first bin that has data, 8 elements, 8 data points fell in that bin. Where in the bin? No clue. Maybe they fell all the way in the left. Maybe they fell all the way in the right. Maybe they fell in the, maybe they're all over the place. I don't know. I don't care because the histogram doesn't care. All that matters is if I fall right on the border between 2, if I get 10, for example, I can't count 10 twice. So does it go left or does it go right? So in our class,
left.
Wow, okay, so right here, borderline cases go to the bar on the right. It's literally in front of you, but thanks for playing anyway.
Okay, sorry.
So I forgive you. So borderline cases always go on the right, not because that's a mandate from God himself or herself or itself, or if you don't believe in that, the great turtle in the sky, but rather because in this class, we've chosen to put them on the right. As long as you're consistent with your choices, it really does not make a difference. Just be consistent. Of course, different bin sizes can create different histogram shapes. And that's one method by which people can present data that's skewed to their desired outcome is the fact that you can represent the same data in multiple ways, and depending on how you represent it might dictate kind of what you conclude from it. So it's possible to come to different conclusions depending on how you represent the data. Of course, I don't have to only list the frequency itself, which is how many. I can also list the relative frequency. That's the proportion. So I can say here, in this case, that 8 of them came in the first bin, or I can say here that 12% of them came in the first bin. What's the advantage of percents? Well, then I can compare different size samples. Because if I have a sample of 1,000,000 and I have a sample of 1,000, obviously the bins for the millions are going to be bigger because I have so many more. But if I look at percentages, then I can compare them in a better way. So yeah, there's that. You can also see whether it's skewed or not from a histogram. This one looks fairly symmetric, maybe a little skewed on the left, but fairly symmetric. Of course, we care about the shape. Is it skewed to the right? Is it skewed to the left? Is it symmetrical, which means a mirror image on both sides? Is it normal, which was the subject of chapter 14, the normal model? Very important stuff. And yeah, so there's all of that. We care about where the center of the data is. So the center is easy to figure out when it's symmetric, but not necessarily easy to figure out when it's skewed. So that comes into the next chapter on median, or sorry, on mean and median. Variability, how spread out the data is. Well, we have numbers for that too, the standard deviation or the mean absolute deviation or the interquartile range. So we have numerical values for those as well. This is certainly skewed to the right. This is still skewed to the right. So we have dot plots, we have histograms, and now we have stem plots. The stem plot is essentially a dot plot turned sideways. You have all the data, but it's done in a slightly different way. With a dot plot, you have 3, 3, 3 in one row, and 4, 4, 4, 4 in another row, and then 5, 5, 5, 5, 5, 5 in one row, and so on. A stem plot is kind of like a hybrid between the dot plot and the histogram, and the fact that you're grouping them together in one column, but you're also not losing any data. And the way we do that is by having the stem, which is the first number of the 2-digit number here, and then all the leaves represent the second digit. So 3, and then 3, and then 3, and then 4, 4, 4, 4, 5, 5, 10, 10, 15, 15, 20, 21, 23, 24, 26, 27, all these numbers. The first number on the left connects to each one of the leaves, kind of like you have a stem on a tree and you have lots of leaves coming out of the same stem. Okay, so we had those 3 representations, and that takes us to the end of chapter 10. So what do you have to know in chapter 10? Dot plots, histograms, and stem plots. You should know how to make them. You should know how to interpret them. You should maybe know when they're wrong, like if there's a mistake in one of them. Okay, all those things are things that you should know. Okay, all with me so far? All right, so that takes care of chapter 10. Now we go to chapter 11. And we start with measures of position, namely the center. So we have multiple, so measures of position is not just the center, but it's where things are located in general. So let's see what we have here. Okay, the median. That's the halfway point. That's the value that has 50% to the left and 50% to the right. It's right there, smack dab in the middle. Also called the 50th percentile because it has 50% beneath it. Also called the second quartile because it has 2 quarters beneath it. So there's 3 different names for the median. The median, the 50th percentile, and the second quartile. In general, I can have percentiles anywhere, like the 25th percentile. 25% is beneath it. Well, that's also a quarter that's beneath it, so we can also call it the first quartile. And the 75th percentile has 75% beneath it. That's the third quartile. So we have multiple names for things, right? The first quartile, the second quartile, the third quartile is the same as the 25th percentile, the 50th percentile, the 75th percentile. But what if I want something besides that, like the 17th percentile? Well, that just means 17% are beneath it. Assuming I can calculate it, go right ahead and use it. And how do I calculate it? Well, it's a little complicated, but we have a method, which I'll show in a second again. So percentiles like the 17th percentile just mean that 17% are to the left of it, are less than or equal to it, and 83% are greater than or equal to it on the other side. How do I actually find it? Well, here's a graph. This is the some example. And you see I start at 0% and I go all the way to 100%. And it always goes up because I have to accumulate. It's a cumulative percentage graph. I accumulate percentages until I reach 100%. So if I said, wait, okay, so where is the 17th percentile here? I would say, okay, well, go here to 17%, which is right here. And my value is 0. So it looks like the 17th percentile is 0. If I want something more reasonable, like the 50th percentile, I would go to 50% right here, cut across to the graph, and I would say, okay, that value is about 25. So 25 will be the 50th percentile, roughly. You can't really see perfectly from a graph, but again, we did examples like these. The median and the quartile, I already mentioned those. The median is the 50th percentile. The quartiles are the 25th and the 75th. We did examples of finding the median, both for odd numbers and even numbers. Know both. Certainly know how to find the median for odd numbers and also know how to find the median for even numbers. Then we had the 5-number summary, the minimum, first quartile, median, third quartile, maximum, and we had this box plot, which denotes those 5 numbers, 2, 3, 4, 5. Helps us see whether it's skewed or not, where the median is, where the Q1, Q3 are, and so on. We also had the modified box plot here, where we don't go all the way to the maximum because it's an outlier. So we make a little dot or a star by it, and we go to the next one, which was not an outlier. So we don't go all the way to that. Oh, it's an outlier. I don't go all the way. I go to here, I stop, and we had the modified, 2 modified box plots and a regular box plot. Examples, more examples, some more examples, more examples, and that takes us to the end of chapter 11. So what do we need to know from chapter 11? Quartiles, percentiles, 5-number summary, box plot. Median, I guess, if you don't want to include that in the quartiles, which you don't want to include in percentiles. 5 ideas. Are there any questions on what we did in chapter 11? No questions on chapter 11. Okay, so let's move on now to chapter 12. All right, chapter 12 was the mean or the average. So the last chapter was the median. This chapter is the mean, or the average. And we had a few different things that we did here. We talked not only about the computational way of finding the mean, which of course, don't get me wrong, is important, but we also talked about some conceptual understandings of the mean, namely as it comes to, well, we'll get there in a second. But first, let's do the numerical value. How do I find the mean? Well, you add up all the values and you divide by how many you have. That's how we find the mean numerically. Is that the best way of finding the mean? As a general rule, yes. Okay, why? Because nothing beats the math. Okay, any other method is semi-conceptual, and semi-conceptual is never as good as just straight up doing the math. But what are the other methods? The other methods are the equal redistribution method, or the Robin Hood method, where you take the values and you spread the values out amongst all of the possible values until they're all even. And then whatever number you have, that's the average. We did the Robin Hood method. We did examples like here with the coins, where you spread out this one too many, so it goes here, and these average out, and you kind of get a value that everyone agrees upon. And then there was the balance point method, where you literally have a physical construction of your distribution, and then you figure out where you can put your finger so that it perfectly balances and does not tip over one way or the other. That location would be the mean, just like the heights for the redistribution method would be the mean. just like the value that you get from the formula would be the mean. So we have 3 different methods for finding the mean. They're all equal. This one, you can either do the redistribution by taking the big ones here and moving them over so that they kind of fill up. Or you can do the balance method where the coins would balance at. Or of course, you can do the regular good old calculation. 0 plus 0 plus 0 plus 0 plus 0 plus 1 plus 1 plus 1 plus 1 plus 2 plus 2 plus 4 divided by how many you have. We did all 3 techniques. Fun times. The next question is, what do? Do we use the mean or do we use the median? Because both of them are important. So which one should we use? The answer is it really depends on the situation. The mean is used when the distribution is symmetric. And the median should be used when the distribution is not symmetric. So very straightforward considerations and criteria for deciding which one you're going to use. Is it symmetric or is it not symmetric? If it's not symmetric, use the median. If it is symmetric, actually it doesn't matter which one you use because you get the same value in both, but use the mean because it is, I mean, when I say symmetric, I don't mean perfectly symmetric necessarily, but if it's close to being symmetric, we would still use the mean. We only use the median if it's really strongly skewed. Like here, for example, this one here is really strongly skewed. I would use the median because this one over here really skews my data. So we did all that. We did this. This is nothing different. It's just another example. The only thing new in this chapter was the weighted mean. What if you want to average 2 things, but they don't have the same weights? So for example, you took more units this semester than last semester. So what is your GPA? It doesn't just average. Your GPA is a weighted average. How do I weight them? Well, because I took 15 units out of the total of 27 units, my 3.0 was weighted by 15 over 27. And 15/27 of the weight goes to 3, and 12/27 of the weight goes to 3.5. I add those 2 numbers up, and I have my weighted average. So you should know how to do that. We only had one.
Wait, can I ask a question?
Sure.
I'm sorry, where did the 27 come from again on that? I forgot.
Total of 27 units, 15 this semester.
Oh, 27 units. Okay, sorry.
All right, so 15 of the 27 were what the 3.0 was for, and 12 of the 27 was the 3.5. So you weight them, you add them, and you have the weighted mean. So that takes us to the end of chapter 12. And then we have chapter 13. So chapter 13 was on variability. And when we did variability, if you recall, we had 4 different measures of variability. Who recalls what the 4 different measures of variability were? Nobody knows.
Enter quartile range, mean absolute deviation, and standard deviation. That's only 3.
That's only 3. There was a 4th. The 4th one was the one that we threw away right away. We said, this is a horrible one, never use it.
Is that the algebra one or something?
Nope. Oh. Nope. Anyone know? The last one was the range. The actual range, the biggest minus the smallest, the range.
Never use it.
No, never use it. Range is horrible. Never use the range. Range is bad. Range is bad. We don't use the range. Okay. But we do use the interquartile range. That's important. We use the standard deviation. That's important. And we don't really use the mean absolute deviation. It was kind of only brought in as a lead-in to the standard deviation, which we do use. So it's the IQR and the SDV that we really use. The range is just bad. It's not very descriptive. These 2 have the same range, but they're very different data. You have one outlier, the range goes up significantly, and no one uses it. But the IQR we do use. When do we use the IQR? We use the IQR when we use the median. If we're going to be using the median, we're going to want to use the IQR. They go hand in hand. You do not use the median with the standard deviation, and you do not use the IQR with the mean. Okay, the IQR goes with the median. It's just Q3 minus Q1. That's it. On the other hand, we had the mean absolute deviation. Oh, so yeah, the IQR is very easily read from the box plot because here's Q3, here's Q1. So Q3 minus Q1, that's your IQR. Big IQR, smaller IQR. The mean absolute deviation was merely a lead-in to the standard deviation. However, it's mathematically easier to work with. So on tests, I may very well ask about the mean absolute deviation. Okay, be prepared for that. The mean absolute deviation is just easier to work with than the standard deviation. So what was the formula for the mean absolute deviation? You look, first you got to calculate the mean. Then you take every data point away from the mean, how far away it is, absolute value. We only want to have the absolute values, add them up and divide by how many you have. That's the mean absolute deviation. The standard deviation was similar and more complicated. You see how far each data point is from the mean. Rather than absolute valuing them, you square them, add them all, divide by n minus 1, not by n, and then take the square roots. And that gives you the standard deviation, which you use with the mean. Why divide by n minus 1? We talked about that. That had to do with the concept of biasness. So we talked about that. And you should be able to look at graphs and determine a relative measure of standard deviation. When values are far from the mean, the ST-dev is high. When values are close to the mean, the ST-dev is going to be low or lower. And this is like an average of the two. So this one will be the highest because most of the values are far away. This is the lowest because most of the values are close. And this is somewhere in between because it's, a mixture of the two. Which do you use? We use the IQR with the median. In other words, when there's a lot of skewness or even outliers. We use the standard deviation when we use the mean, which is when it's symmetric. Okay, so that's it for chapter 13. Any questions on that one? Hopefully you're all still here paying attention. I don't know. I know Lori is because Lori's amazing.
You're so nice.
Okay.
Thanks. I'm just saying I have to fake it till I can make it.
Fake it till you can make it. Yeah, I see you as well.
We're here.
Wait, where's Math Baby?
Where is
Matt Baby went back to his grandma, but he was here for the
Aw.
first 30 minutes, and we were calling your name.
we
Darn.
will. And
I
my
missed that.
I'll bring him before we leave.
Okay, great. Thanks.
It's in the front house.
Okay. And of course, where are all the dogs, right? Everyone had these little awesome dogs. I don't even see anything anymore because I just see like 5 of you. Any dogs hanging out anywhere?
What for if you have your big ass TV now?
Yeah,
Wow. Wow.
I second that.
My big ass TV.
You got a new TV, huh?
Pardon the French.
A new TV. It takes up like the entire room.
No, it's not.
Where?
It's a teeny weeny TV.
It's not a TV. That's my TV.
Lori, you want to know why we started at 2:30? Because they were putting his TV up. He took
Hold
our
on a second.
education
Hold on,
away
hold on,
from
hold
us
on, hold
for
on.
his TV.
I didn't.
That's okay.
I didn't
We
schedule.
got the priorities
I didn't
straight.
schedule it for class time. Okay, you know these things. They're going to be before between 12 and 8. Okay, I had an 8-hour window that happened to come right in. Okay, what can I do?
Yeah, Brian showed up unexpectedly, and you have to give him your number.
Yeah, Brian was amazing though. He liked to talk, but he liked to show me some things, so I don't mind. Okay, so chapter 14, the normal model. The normal model is extremely, extremely important. The normal model deals with distributions that are bell curved. These things come up all over the place in nature and in life. Pretty much most natural processes, I want to know most, but many natural processes are normal shaped. So very, very, very important. And we had some rules about normal distributions. I gave you the 68, 95, 99.7 rule. If you go one deviation either direction, that's 68% of the data is going to fall in there approximately. If you go 2, 95%. If you go 3, 99.7%. The acronym almost all means 99.7%. It's unusual if it's out past 2 deviations. Am I ignoring Angela? Why would I ignore Angela? Did she say something? Hold on. Show and tell. Show and tell. I just showed you my TV. And I showed you Brian, who was hooking up my TV. I'm done. I'm done my show and tell. All right. So you want to show and tell, you show and tell. What do you want to show? How about not today? Because we have a test to study for it. But and I wasn't ignoring her. My chat was covered by people, so I didn't see it. So I really apologize.
You mean by your video game?
Sorry, what?
You mean it was covered by your video game? Don't pretend it's not in the background running.
It's the same screen. That hasn't changed.
On your computer.
Oh, that. Well, yeah, that goes without saying. So anyway, when we use 95% means 2 deviations. That means within 2 deviations, you're going to have anything outside of 2 deviations is unusual, but almost all means 3 deviations. And we talked about z-scores. Okay, z-scores. First of all, we had a formula for z-scores, which you definitely have to know. I mean, 100%. I'm going to ask you a z-score question on the test. Okay, z-scores are such an important part of statistics. You take your data, you subtract the mean, you divide by the standard deviation. But what does it mean? What does a z-score mean? It tells you how far you are away from the mean in terms of standard deviations. So if your z-score is 1, you are 1 standard deviation above the mean. If your z-score is 2, you are 2 standard deviations above the mean, and so on. It tells you where you are in terms of standard deviations. Very important, or as they say in Hebrew, muy importante. So this way we can actually compare different distributions. Like here is our future president and his wife, and we have a situation where we're curious which one is taller. Now, of course, Mr. President is taller than the First Lady. There's no question about that. Just look, you can see. But the question is, how does he compare?
Newsflash, he didn't win.
He didn't win? I said future president, not the president this time. I can wait 4 more years.
Okay, yeah, next time.
I'm sorry, too political. I apologize. Okay. So the question is, how tall is he compared to his peers, and how tall is she compared to her peers? Well, if we look at his z-score and her z-score, we can say, well, his z-score is higher, or her z-score is higher, and therefore he is taller relative to his peers than she is. Z-scores allow us to compare across multiple demographics. Z-scores also allow us to get to percentiles. Remember, when you have a percentile, that means that percent is beneath it. So if my z-score, for example, is 0.8, that means that I'm over here, 0.8 deviations above the mean, and it means that 78.81% of my data is to the left. So I'm at the 78.81st percentile. Z-scores correspond directly to percentiles. Z-scores also correspond directly to raw data via this formula. So Z-scores connect to everything, raw data, percentiles. And we also did after this T-scores. Z-scores connect to everything. So if I give you a T-score and I say, what's the data? Or if I give you the percentile and I say, what's the T-score? Always go through Z. It's the center. Z connects to T, Z connects to raw data, Z connects to percentile, but they do not connect to each other. Okay? So this takes us to the end of homework number 14, and it takes us to the end of our review, almost right in time. 6 minutes to spare, which is perfect, just about, so I can answer questions in the remaining 6 minutes.
Little off topic. How many more chapters will we cover, do you think?
Well, we finished 15, I think, by this point, or maybe we finished most of 15. I don't recall if we actually finished it or not.
We didn't.
There are a total of, I think, 23 chapters. But we also have only 8 more class periods. Now, do we have class
Wow.
next Thursday?
It's Veterans Day on
For
Wednesday, so
Thanksgiving, I don't think so.
No, it's not Thanksgiving. Oh, we're not going to have Thanksgiving either. Maybe that's what's going to happen. Maybe the Wednesday class gets off for Veterans Day and then the Thursday class gets off for Thanksgiving. Maybe that's how they do it. So that means that we have 4 weeks after today. And 7 of those will meet because the other one is Veterans Day. When is Veterans Day, by the way? November what?
11.
Which is Monday.
It's a Wednesday.
Oh, it's a Wednesday?
Uh-huh.
That will not affect us. Now, I'm not going to be here this coming Tuesday on November 10th, but unlike the last time where class was canceled, I'm going to try to get a sub because I don't want to like lose pay. And this will be good also so that you can see another teacher and decide how amazing I am compared to another teacher. Because right now, if I'm the only one you have, you might be like, she's average. She's like what all teachers are. And it's kind of like, nah, well, you'll have someone else and be like, oh my God, this guy's horrible. And I will take the risk that he's better than I am, and what you're going to say, oh crap, why don't we take him instead? I will take that risk. I am willing to take that risk. But I will not be here on Tuesday. So I will.
Professor,
Yes.
what if we don't like the way that person teaches?
Wow. Sucks to be you, doesn't it? You don't like the way I teach. What do you want to do, huh?
No, I love the way you teach.
Oh, fuck.
Lori, let me go bring baby for you. Hold on.
Okay, I want to see baby.
All right, babe.
Professor, why don't you just do a pre-recording of yourself and put it up so like that we can have that as a reference?
That's a great idea.
Just put up your Monday one from the
Yeah.
class.
That way we don't risk
Perfect.
liking or disliking someone else.
Right. We don't want to be stressed out by having to deal with a different professor.
Okay. All right. These are good ideas. They're not horrible ideas. Okay. I just have to get permission. Okay. Because if I just don't come on Monday and do this,
You could still get paid. You can.
no,
My
I gotta-
sped teacher does it all the time.
who does it all the time?
I mean, not all the time, but he has lectures. We're not meeting. We're not meeting on on Veterans Day, but he's going to have a video. Oh, there he is.
Hello.
Hi, math baby.
Liam.
Hey, Liam. Oh, he knows his name so well. Look at his little hairdo. I love
Oh,
it.
I know my name, but no one ever says anything about that. Okay.
He's so cute.